can prove that they have certain strong identifiers associated with each other, and also do it efficiently. So very quick, analysis is analysis comparison. If you see that the amount of exponentiations that we need are constant for provers, which is very nice because it's the provers that are constrained with devices and stuff. So as compared to other techniques which do not use aggregation, in our case, the T over here corresponds to the number of identifiers being proven. So these are the factors in the multifactor. So we do not depend on that amount, the T, and the provers can efficiently create these proofs, and this verification can also happen quite efficiently in most cases. Others, it's comparable. Another thing which you may probably not see if you haven't seen the protocols is the storage requirements. In most of the current aggregation techniques in zero knowledge, they require the kinds of combinations to be predefined. In our case, we can combine it in any form during the runtime, during verification. In the other cases, they require the user to store all sorts of combinations. And if you can think of it, there will be exponential number of those combinations if you want to store all sorts. So that is very nice. So I know these are like deep crypto things, and it's hard to get into it at once. But if you have any questions at this point regarding the crypto protocols, I'll be happy to answer. Or you can think of it and we can talk about it in the end. So at this point, we'll switch gears and go to talk about some of the biometrics and how they integrate in such cryptographic protocols. Biometrics have been there for a while, and they have been investigated in several ways. But integrating them in cryptographic protocols is hard, because if you take a biometric and you record it twice, it is most likely that those two recordings are slightly different. There's a certain amount of noise which does not make it. It's not straightforward to use this biometric reading for cryptographic protocols. What is traditionally done is that the biometric is captured, and certain features are extracted. So once you extract the features, a template is created. A template is essentially digital encoding of a biometric. And then it is, at the time of enrollment, it may be stored at the client or the server. Different problems exist based on where it is stored. And at the time of verification, there's a probabilistic matching. So it is matched against the stored template. Okay? So one of the biggest problem here is the template itself. Like, regardless of where you store it, if this template is compromised, then you can potentially misuse this biometric, or you can link it to other databases where you can retrieve more information about this user which was outside the intended purpose. Okay? So one of the things that has happened recently is to generate keys from these biometrics. So the main idea behind generating keys is to first take the biometric and convert it into some kind of a bit string. So this bit string should have two specific properties. Okay? The bit string should have large inter-class variation. It means that you and me should have different bit strings. We should not generate the same bit string. So it should have large inter-class variation and small intra-class variation. That means that if I record a bit string twice, it should be close to each other. This closeness is really determined in the second phase, where you have a bit string and you use some metadata and boil it down to one key. So if two instances of the bit string are similar, so it's from the same person, then the same key should be generated. Okay? In our system, this is the main flow. In the first phase, what we do is we take various types of biometric images, and this is like face, iris, fingerprint images, and we use singular value decomposition. This is a technique to extract the most significant features of an image. Many of you might have done it in linear algebra. And basically, you do this singular value decomposition and extract the main feature vectors of this particular biometric. So a person who records his biometric twice will have similar this biometric key hash vector. At the time of the second phase, what happens is that you take this hash vector and use a classifier to classify this particular hash vector. And in this whole process of classification, we generate a particular key. This biometric key is the strong identifier that we used in the original the zero knowledge proof protocol. So we commit this this biometric key along with another random, which is used again in the zero knowledge proofs. So let's go into a little bit more in depth of how this particular hashing is done. The procedure is rather interesting. If you see, the input image is taken, and then various aspects, the various parts, sub-images of the original image is taken. So these squares are selected pseudo-randomly based on some secret. And each of these squares are associated with, are basically converted into a matrix, which is used to extract the most significant features, which are called the eigenvectors. So we take the largest eigenvectors for each of these sub-images. Then these are pseudo-randomly combined to form a secondary image, which is again used with the singular value decomposition to get the final hash value. So just to understand what does this SVD mean, it's basically for each image, it's broken up into two orthogonal matrices, UI, VI, which is basically kind of taking the most significant features of AI. So at every point you can think of filtration, like you take the best parts of an image, you combine them together to form the secondary image and do the same process again to get the final hash vector. Now this hash vector is a point over here in this classification model. So this classification model has a lot of users, and this one point corresponds to one hash vector. So at the time of key generation, what happens is that this particular hash vector is ranked, and based on the confidence degrees of a support vector machine. And the biometric key is the highest confidence degree, which is the class of this particular hash vector. At the same time, it also takes the top n by 2 classes. If you think about it, if an attacker gets this particular classifier model, and he's trying to guess the key based on this model, the number of choices that he has is first to choose the topmost class, which is 1 out of n, so n, and a combination of nt, the NCT I call it. So if you calculate for n greater than 69, the number of choices for an attacker to choose a biometric key would be greater than 2 to the 64, which is the lower bound of what is considered computationally hard. Yeah. So we looked into some, we actually tried to get evidence if these algorithms work. So we looked into some thermal optical sensor fingerprint samples and iris samples. We also found some nice face samples. I mean, you can see the differences. One is very straight, very easy to recognize. The others are have a certain amount of noise. And the results were pretty reasonable in the sense that the thermal did better than the optical, as you can see. Then the iris did well too. In the case of the face, it was less than 2% of a change, even if we had more noise in the second set of samples. Then we also looked into the uniqueness and the repeatability. So I talked about the interclass and intraclass. So this is basically a ratio of the interclass by the intraclass distances. So the main idea here is that we need large interclass distances. Two different people should be very different from each other. So this number would be big if we had large interclass distances and small intraclass. So the same person is able to regenerate their biometric key at different instances. So we got some big numbers over there. Then the final set of results, a summary over here, is that we got biometric keys of length from 64 to 214 bits, depending on the number of classes that we had in the last classifier model. And we tried to synthetically increase the number of classes by adding some spurious classes. And there are some very interesting things here, because you can look, if you add random classes, then we try to see ways that an attacker can identify a random class from the real class and so on. So there were some interesting aspects here as well. But if we analyze the system a little more, there are a few most important things. We have the biometric image, which is the main biometric. Then the secrets that we have is a hashing secret to choose those squares that we saw while the hashing process happens. So there are some hashing secrets. Then we have the model, the classifier model. And from all this, we can generate the biometric key, and which is used with the commitment secret, the random R that we used to commit a particular identifier